Hello, my name is Martin Trommer. Welcome to this video abstract for my PhD thesis, where I was studying the effects of solid-state inclusions on the reactivity of uranium dioxide. Why was I doing that? Well, every country that uses nuclear power has to take care of spent nuclear waste. Why is that important? Well, that's because of the high radiotoxicity of spent nuclear fuel, and the environment has to be protected from it. While there are many theoretical possibilities of dealing with spent nuclear fuel, most countries are planning to use deep geological repositories. And in Sweden, this repository will consist of 4 barriers, with the innermost barrier being the spent nuclear fuel itself due to its low solubility in groundwater. But there is a problem. It is very difficult to study the reactivity of spent nuclear fuel, or at least to understand what causes different effects. So what I was doing is to start from the most simplest system, which is pure UO2, and then by doping it with different substances to partly model the behavior of spent nuclear fuel. In my work, I was using palladium as a model substance for epsilon phase metal particles, and yttrium oxide as a model substance for rare earth elements in spent nuclear fuel. But now, since my time is over here, it's time to go home for a last time, and I want you to follow with me. What a nice Swedish summer day. The pellets I've just told you about, I was performing 3 different kinds of experiments with them. In the oxidative dissolution experiments, I used simulated groundwater, in my case 10 millimolar hydrogen carbonate solutions, and put the pellets just in there, and an oxidant hydrogen peroxide in my case. And then I was studying the release of uranium-6, corresponding to the dissolution of the matrix, and the consumption of the oxidant hydrogen peroxide. With these 2 values you can then calculate the dissolution yields, where you actually see how much hydrogen peroxide goes to the oxidation of uranium-4. The rest cannot be studied with this technique. So I did some mechanistic studies to measure OH radical production, which is the assumed product of the catalytic decomposition of hydrogen peroxide. And even with these methods you cannot study everything, so I also used some electrochemical studies to find out more about this system. And in this case I used cyclic voltammetry, I used linear polarization resistance experiments, and I also measured their corrosion potential. But now it's time to get the train. So, we have around 2 minutes till the train goes, so I can shortly tell you about some results. The palladium doped pellets, it showed that palladium catalyzes both the oxidation of uranium-4 and the reduction of uranium-6. And the reduction of uranium-6 was diffusion controlled at a rate constant of 10 to the power of minus 6 meters per second. In a system with 40 bar hydrogen, 1% palladium was necessary to suppress oxidative dissolution completely. Under inert conditions, during gamma radiolysis, where hydrogen is just produced radiolytically, already you need 3% palladium. When you add 1 bar hydrogen in the radiolytic case, just 0.1% palladium is enough to suppress oxidative dissolution. The pellets with yttrium oxide showed that yttrium is capable to reduce U6 dissolution significantly, and this cannot be explained by pure competition kinetics. Furthermore, it was shown that yttrium influences the redox reactivity but does not have an effect on the catalytic decomposition. So, I think we should get into it. Hello, welcome to Großstadt. A few more minutes and we're home at my place. Besides experiments, I was also performing numerical simulations on the effect of solutes on radiolytic production of hydrogen peroxide. I was looking at hydrogen, hydrogen carbonate, iron 2 and 2-propanol. Hydrogen and iron 2 will be available in huge quantities once the canister starts corroding at the time of failure. Hydrogen carbonate is available anyway, and 2-propanol as a model for the organic substances in groundwater. All of them, it has been shown that they can affect the radiolytic production of hydrogen peroxide. Hello, welcome to my place. There is only one thing left to do. I would like to tell you the 4 conclusions you can draw from my work. Number 1. The palladium-catalyzed reduction of uranium-6 on the surface by hydrogen is the most important reaction in the suppression of U4 oxidative dissolution. Number 2. Yttrium oxide also has an effect on that. It was shown to significantly reduce U4 oxidative dissolution under hydrogen, but also under inert atmosphere. Number 3. The amount of hydrogen not consumed in oxidation of uranium-4 is consumed by catalytic decomposition, leading to OH radicals. Number 4. Numerical simulations have shown that hydrogen is able to suppress the radiolytic production of hydrogen peroxide, and that the amount of hydrogen necessary to do so depends on two things. 1. The amount and types of solids in solution, and number 2. The dose rate. My name is Martin Trummer. Thank you for watching. Good night.